3,000 tons of that, whereas NF3 I think is in the range of 2,000 to 3,000. And you can look those numbers up, and I guarantee what I gave you was wrong, but it was in the ballpark or in the range. Okay. All right. So now, did anybody have any other questions before we go on?
Doctor, can we close it? Where is the controls?
No.
It's.
Okay, so we're just working on the lighting here a little bit. So I'm going to go ahead and we've got the process gas coming down, and I'm a very terrible drawer, but okay, so. Or whatever. So what we've got is we've got the process gas coming down. Stage 2. 2 CDA. And then right down here, drew this wrong. I'm going to have to erase some of that. Sorry, I'm having technical difficulty. Okay. Okay. Okay, so now what we're going to have is we're going to have about 1 to 2 liters per minute. 6, 7, 8.
So 1 to 2 liters per minute saline you're talking about?
Clean dry air.
Clean dry air, okay.
Okay, so now what we've got right here is we've got the silane from your process gases coming down here.
Okay.
They come in, and you've got the stage 2 CDA, and most of the students, I've already pointed it out to them on the machine. And we'll go downstairs and we'll take everything apart and what it looks like on the inside. This is 6 to 8 liters per minute. This is a tube that actually goes down, and about halfway in the middle of this is where it actually injects the 6 liters per minute of clean dry air, right? In the very top, stage 1, you get 1 to 2 liters per minute of clean dry air right up here. So what you've got is right here, you've got a small injection. It's going to mix with the silane and have a small reaction. And then the stage 2 is going to be a larger reaction mixing with the silane. Now, on the outside here, what we're going to end up having is we discussed it out there and we showed it to you guys, but there's going to be a water cooling jacket right here. And what this does is it provides just cooling flow for the reaction that's occurring in here. So now what this system does right here, we've got silane coming down. Silane coming down. We've got our first stage, our oxygen source is the CDA coming right in here. The second stage as our oxygen source is the CDA. And the reaction occurs into 2 places. Now, that's exactly it for the oxygen source, what you're going to actually react out your silane. Okay, so now what we've got right here.
So this is a requirement even if we have a very little silane or very lot of silane?
You know, what's going to end up happening is the system is designed to stop you from having a problem. Okay? So now with the purges and the reaction that occurs inside of here, under any conditions, this system guarantees that you have less than 1/10 of LEL of silane on the outlet of this system. So if you've got a very, very small quantity of silane, then it's probably not going to do anything. There will be no reaction occurring inside there. If you've got a large quantity of silane, then what this does is this system will react the silane in a safe manner to prevent you from having explosive compounds in your ductwork. Does that make sense? Okay.
So for silane levels of let's say up to 50 SCCM, 50 is come. So the system is pretty easy to handle it then.
under normal conditions and the flow rates that you've been talking about, combined with the pump purges, which is going to be between 30 and maybe 50 liters per minute, right? Plus the purges on this, you're going to end up, plus the amount of silane that's used up in the process, you're going to end up with very low concentrations coming into the scrubber. And so, under normal conditions, you'll have some of it will always react with the CDA, but it's not going to be a high efficiency scrubber as far as the silane goes. Okay, but if you have, let's say you have an accident where you're doing an MFC calibration with the chamber cold or something like that, then this scrubber will make sure that even if you're having a high percentage of silane coming in, then it will be safe on the outlet of the scrubber. Because then you'll get a very high efficiency reaction going on in that entry.
Okay.
Does that make sense? Okay, thank you.
Yeah, but my point is that so we don't have any, just 50 SCCM falls into the operation of the system, right? It's up to 50 SCCM.
Oh, it could go much higher than that, several liters.
Much higher than, okay.
Yeah.
What about hydrogen? Basically, we had another question about hydrogen.
What kind of flow rates of hydrogen are you talking about?
The maximum flow rate, we are talking about 500 SCCM.
Okay, if you combine that with the pump purges of say 30 liters per minute, plus the purges that are coming into this scrubber, your exhaust is going to be half liters by 300 liters probably in total, right? So that would be put you well into 0.25% of hydrogen or less, and the LEL for hydrogen is 3%, right?
So hydrogen will be any problem.
Yeah. Okay, so any other questions on that?
No.
Okay. So now, go ahead. So we've got the entry. I'm just going to draw that as a block on the top here. Okay. Okay. There we go. Okay. There you go. Okay. Then we've got okay. Okay. All right. So now, this is a very crude drawing, but what we have right in here is we've got the packing media, right? We've got the pump that recirculates the water up here. We've got a spray bar. The spray bar rotates, right? So the spray bar rotates. It sprays water down onto the packing media. The packing media provides a wetted surface area. You notice just a whole bunch of balls, and the water flows over the balls, and the surface of the balls is designed to be wetted. Now, the efficiency of a wet scrubber is determined by the square meters of wetted surface area and the amount of time that the actual process gas is able to spend in here. As you can see, you've got a 50 liters per minute coming in. You've got a small purge. Let's see from the. Oh. So you've got the pump is coming in here with 50 liters of gas, plus your purge is coming in there, and you've got 150.